This video is about specific heat capacity. So it's important that you've had a look at the video on specific latent heat before this, so you understand how that term is different. The equation for this is slightly unique because it's obviously got three bits on one side of the equation, so it means that rearranging is something that often people struggle with, so we need to have a look at that too. So when we're talking about specific heat capacity, we're talking about the energy transfer between one material and another. So if you imagine, first of all, imagine that I've got like a ball on a slope. If I've got obviously a steeper slope, the ball would roll faster. In much the same way, if I've got a difference between a high temperature and a low temperature, and that difference is bigger, and we call that difference the temperature gradient. So if the temperature gradient is quicker, heat will be transferred faster from one place to another. So how easily something can absorb energy and store energy is very much to do with specific heat capacity. So it's made up of three words. Specific means per unit mass. It means divided by mass. Right? When you rearrange it to give a specific heat capacity, that's what you get. Heat, because it's thermal energy, and capacity, the ability to hold or the ability to store. So we can think of it very closely linked to how much energy is stored in a particular material. So if we rearrange the equation, what we quite often do is rearrange it to give a specific heat capacity, which is C. So it's mass times specific heat capacity times the change in temperature. So a change in temperature is the final temperature minus the initial. So it's very important that this triangle here, you understand, is the change in. So if we rearrange it, we get that energy divided by mass times the change in temperature will be equal to the specific heat capacity. So that's why we mean per unit mass, because it's divided by mass. It's energy per unit mass times change temperature. So how we define it is how much energy as heat is needed to increase the temperature of material by 1 degree. So water has a specific heat capacity of 4,200 joules per kilogram per Kelvin, or per degree C. What that means is that you need 2,400 joules of energy to heat up 1 kilogram of water by 1 degree. So that is our definition. Specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree. And each material will have a different specific heat capacity. And again, I want to refer to the fact it's like analogous to how much energy a material can store. Obviously, water has quite high specific heat capacity, and that means it can store a lot of energy, and that's why we use it for central heating in our homes. Let's have a look at the actual equation, how we use it in a question. So remember, whenever you're doing calculations, we have 4 steps. So step number 1 is to write down what the question has told us. So we're calculating how much energy, so energy is a question mark, is required to heat 2 kilograms, that is our mass. So obviously we put kilograms of water from 10 degrees to, so from and to are useful words because it indicates the change in temperature. So a change in temperature, of course, is only 90. And then the specific heat capacity of water is 4,200. So straight away, we then do step 2, which is we write the equation. Now this is a really easy equation to use, remember, because it's only one equation with specific heat capacity in. So anytime you see this phrase, specific heat capacity, in an exam question, and then there's a number followed by it, and take note of the unit, you know you're going to have to use this equation. So then we put our numbers in, and don't forget it's a change in temperature. So 2 times 4,200 times 90 gives us 756,000 joules. So why is water used in our central heating? Well, because it can store an awful lot of energy. Aluminium has a different specific heat capacity. So let's have a go at working out what that would be. So we underline the key bits of the question. We have 200 grams. That has to be in kilograms, so we're going to need to change that. It cools down from 115 degrees C to 10 degrees C. We need the difference between those, and we're losing 19,068 joules of heat energy. What is the specific heat capacity? So energy, mass, which we've converted into kilograms. So remember, to convert it from grams to kilograms, you divide by 1,000. Specific heat capacity is what we're working out, and our change in temperature is from 115 to 10. So we write our equation. We then have to rearrange it because we now need to work out specific heat capacity, which I did before, which is E divided by M times delta T. We then put our numbers in. Notice the change in temperature being 105, and then we get our answer. And the last stage, don't forget the unit. So specific heat capacity has units of joules per kilogram per degree C. So those are our units. You can see aluminium has a much lower specific heat capacity than water. It stores a lot less energy, which would make sense that it's easier to heat up a metal, and obviously metals cool down a lot quicker than, say, water. So the last thing on specific heat capacity is you need to be aware of the experiment that we use to determine specific heat capacity. So if we're determining the specific heat capacity of a block of metal, so this is a diagram. We have our block of metal. We need to put a temperature sensor or a thermometer in there, and we have our heater inserted in there. So when we do this experiment, there are 5 measurements we need to take. So the first is we need to measure the mass. So we use scales to do that. The second is we need to measure the temperature so that we have the temperature change for our graph. What I want to do is I want to then work out how much energy is transferred to the block, which I can't do directly. So I do it indirectly by working out instead the power. And we do that by connecting an ammeter in series and measuring the current. So this heater here is connected to a circuit, and you connect that to an ammeter. So obviously an ammeter with an A in it. And we also have to connect across the heater a voltmeter to measure the potential difference across the heater. Obviously we also need a power supply, so it's a battery that we connect like so. Okay. So we need to measure the current using our ammeter and the voltage using our voltmeter. So we measure the current and potential difference. And the last thing is I need to time how long it takes the block to heat up, because power is energy divided by time. So the energy is going to be the power multiplied by the time. Obviously electrical power is current, which is I times V times P to give us energy. So that is our electrical power of the heater, electrical energy transferred by the heater, and then so that's the top part, and we divide that energy by the mass and the change in temperature. If you plot this as a graph, you get a graph that looks like this. So we have time, and when you can see at the start here, because of the limitations of the experiment, there is a lag time, because obviously heat has to transfer from the heater to the thermometer, so that takes a couple of seconds for conduction to start to get through. And then we get this bit. So here, between this section, we can then work out the gradient of that because it's a straight line. You also notice that after we switch the heater off at this point, it actually continues to get hotter. That's again because there is heat still being transferred to a temperature sensor even after we turned it off. So the way we account for that is you can use the maximum temperature and read that off your graph in order to give you the most accurate energy transfer, or you could just do it over a constant period, like so. The limitations of the experiment is obviously this glass metal block is going to lose heat to the surroundings, so you want to try and insulate it in some way. It's really important that here the thermal contact between the heater and the block is as good as possible, because obviously if there's air in that gap, you're going to be heating up the air, not the glass block, and your calculations will be wrong. So insulate the block, make sure the heater has a good thermal contact, account for the lag time, and lastly, you can see in the diagram the heater is fully inserted into the glass block, and quite often they stick out the top. It's really important it's fully inserted into the glass block, so that again you're not just heating the air surrounding it. So you should be familiar with this experiment, and just again I just want to reiterate the key point. So you need to know what quantities you are measuring, so mass, current, potential difference or voltage, time, and the change in temperature, and the equipment for that. So a voltmeter, an ammeter, a timer, some scales, and a thermometer or a temperature probe. And then to work out specific heat capacity, we rearrange the equation like so. You can work it out from the graph. The gradient of this graph is temperature divided by time, and obviously we need time over temperature. So if you do the voltage times the current divided by the mass and then times it by 1 over the gradient, you can also work out specific heat capacity.